Now let us change the rules of the game a little bit. So maybe take a note that the coefficients at xy 0.005 and 0.002 here in the previous example, and now this one is bigger, 0.014, a little bit bigger, and this one also is a little bit bigger. Oh, like 5 times bigger. Well, anyway, so compared to the previous example, we haven't changed the intrinsic growth rate and we haven't changed the carrying capacity. So we only changed the coefficients at xy in both equations, which means that the presence of y became worse for x and the presence of x became worse for y. So essentially it means that the competition is fiercer, so is tougher. What we expect, of course, if the competition is tougher, then even if the equilibrium population exists, then at the very least, the equilibrium, both populations, both tigers and leopards, are going to be smaller, right, if the competition is fiercer. So let us see if that's true. And if we calculate the equilibrium, again, the answer is now x is 10 and y is 5. Instead of 20 and 8, we got 10, 5. So at least it is consistent with the intuition. So both, there exists an equilibrium, but both populations in the equilibrium, they became smaller as compared to the previous example. The other three are, of course, the same, because the other three are just 0, 0, and carrying capacity and 0. And carrying capacity hasn't changed. And so the only thing that is changed now is the competition. And now, notice that something is very different. Not only the equilibrium populations became smaller, but the type of the critical point is also different. I think you can guess now, but imagine the following. So suppose that, as I said, this is ecology. So suppose that the system stabilized at 10.5, but then something happened. And for example, suddenly the conditions became better for both the species. But imagine that suddenly because of some external influence, the populations changed a little bit from 10.5 to a little bit more than 10.5 for both of them. So here. But then the two populations are going to eventually, according to the differential equation, go along this line, along this solution, and then boom, x survives, but y dies out. On the contrary, if, say, the conditions became worse for both populations, but maybe the equilibrium moved here, and now if we just follow the arrows here, then boom, now something different. Now x disappeared, but y survived. All right. Now, if we calculate the type of the critical point at 10.5 from the Jacobian matrix, again, here is the Jacobian matrix, and substituting the specific values 10 and 5, we get a matrix with specific entries, and then its determinant is negative, and as we saw before, it is a saddle point. So the critical point 10.5 is a saddle point, which means it is unstable. But also the saddle point has this nice property that how exactly it is unstable is not clear, right? So then what we see here is that depending on the initial condition, one of the species is going to die out and the other one is going to reach its carrying capacity. That's the prediction from the model, right? So if the initial condition is somewhere within this region, then the first species survives. If the initial condition is somewhere in this region, then the second species survives. And of course, there is a fine line in between, which I am not teaching you how to calculate, but you can read the textbook a little bit further. Section 9.7, I think, is exactly about how to calculate this fine line between that separates initial conditions when the first species survives from the initial condition where the second species survives.